Hi guys, Dr. B here. So this lecture is dealing with something called periodic trends, and periodic trends refer to the periodic table. This is continuing with our understanding of codes, being able to analyze, etc., interpret. So like I said before, I don't expect you guys to memorize the periodic table. I expect you guys to be able to use the periodic table as a resource to be able to interpret it in the following ways. So this is just the graphic organizer that I have for y'all on Google Classroom. And it's just a different way to kind of group these three trends. The one that you have is very blank, obviously, so I'm not expecting you to draw everything or write down everything, but I want you to be able to have the definitions and make sure you guys have a few examples that help you understand how the trends work. So the following terms, period and group, y'all should know these already, but make sure you know them if you don't know them yet, because if and when they come up in the lecture and during class, if you don't know it, you're going to be pretty confused, and it may prevent you from understanding the trends. So a reminder what a period and a group is. A period is a row, a group is a column. So atomic radius, the distance from the nucleus to the valence shell. Okay, so looking at this, it increases as you go down a column or go down a group. It decreases as you go across a period or a row. So yes, you should know the definitions. That's not enough. Why? I don't like, oh, it goes down. Well, why when you go down a group, why does it increase? When you go across a row or a period, why does it decrease? Okay, that's what I want you to figure. What's what I want y'all to get from the lecture. So the idea is, as you go down a column, like we'll go down like here, why is it increasing in radius? Well, it's increasing, the atomic radius increases because you're adding more orbits every time you go down. So like even like it's 1s2, 1s1, 2s1, etc. The outermost shell is getting further and further away from the nucleus. Why does it decrease? For the most part, as you go across the periodic table, across a row. Why is it decreasing? Well, keep in mind that you are adding more valence electrons. So adding more valence electrons is pulling the valence shell closer to the nucleus. So by pulling it closer to the nucleus, you're decreasing the radius itself. So I didn't write down everything, obviously, that I'm saying, so make sure you guys are paying attention to this, okay? So this is just a quick diagram to show this. So remember that it increases as you go down a group or a column because you're adding more shells. That's what's being shown here. So again, let's try to interpret this graph. Your x-axis is the atomic number. It's supposed to be an x. Your y-axis is your atomic radius. So why is it increasing? Why does it dramatically increase here, 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 and here? And why is it decreasing as you go here? Okay, so just kind of keep those. You should be able to know. You should know why. But what's happening here that is actually increasing the atomic radius. It increases as you go down a family and decreases as you move from left to right on a period. So examples, what is the largest atomic radius and why? It should be francium or Fr. Why? Because, and don't say it's because you're going down. I'm not looking for that, because you're just repeating the trend, which is more, it's like the most basic answer you can give, and I'm not looking for that. It increases because you're adding, or because it has the most orbitals, and least amount of valence electrons between rubidium and xenon and potassium and francium. Okay? So you can say, well, you can answer this any way you want to. So which one is the larger, has a larger atomic radius for this? It is rubidium. So this is going across a period. It's rubidium because these two have the same number of orbitals, but rubidium has the lesser number of valence electrons. Potassium and francium, which of the two has a larger one? So francium, because francium has the most, has a higher number of orbitals, but they have the same number of valence electrons, so keep that in mind.